Greetings and welcome to Talk a Little, Learn a Lot, the American Society of Naval Engineers podcast, during which we talk about all things ASNE. I'm your host, Stephen Phillips. Today, I'm joined by Rear Admiral Tom Druggan, U.S. Navy retired, to discuss the digital story of Aegis, 15 years later, and the future of the Naval Engineers Journal. A native of Lexington, Kentucky, Rear Admiral Tom Druggan attended the U.S. Naval Academy in Annapolis, graduating with a Bachelor of Science in 1989. He attended the National Defense University's Eisenhower School, graduating in 2006 with a Master of Science in National Resource Management. He also attended the Naval Postgraduate School in Monterey, California, graduating in 1995 with a Master of Science in Operations Research. At sea, Druggan served as commanding officer of the Aegis ballistic missile defense destroyer USS O'Kane. He also served as executive officer of USS Lassen, commissioning combat systems officer aboard USS O'Kane, and combat systems officer aboard USS Elliott. He completed his initial sea tour as navigator and anti-submarine warfare officer aboard USS Callahan. Ashore, Druggan's Pentagon tours include Special Assistant to the Chief of Naval Operations, Special Assistant to the Vice Chief of Naval Operations, the 2001 Quadrennial Defense Review Staff, and as a founding member of the Navy Operations Group Deep Blue. After command at sea, Druggan served in Program Executive Office for Integrated Warfare Systems. There, he supported carrier combat systems and was then selected as a major program manager, serving as the major program manager for fleet readiness and then Aegis combat systems. Druggan's first flag officer assignment was as Commander, Naval Surface Warfare Center, located at the Washington Navy Yard in Washington, D.C. In this position, he led more than 17,000 scientists, engineers, technicians, and support personnel, both civilian and active duty, stationed at 8 Naval Surface Warfare Center divisions located across the United States. Druggan was also assigned additional duties as the Department of Defense Executive Manager for Military Explosive Ordnance Disposal Technology and Training, with oversight responsibilities for joint military EOD systems and training. Finally, for his last 4 years on active duty, Rear Admiral Druggan was the program executive for Aegis BMD at the Missile Defense Agency. Admiral Druggan, Tom, thank you for joining me on the podcast. I look forward to our discussion.
Thank you, Steve. It's a real pleasure and an honor to be here, spending some time with you, talking about Aegis. And I've always been impressed with the ASNE organization. Many don't know, but this is one of the oldest professional societies in the United States. Frankly, the ASNE records and periodicals going back centuries is literally a treasure trove. And it's the story of America. I mean, we're a maritime nation. Our highways, our super highways, were the rivers. It all speaks to the contribution that ASNE has made throughout our country's history. And I'm honored to be here today. And I'm honored and then looking forward to talking about some Aegis here.
Tom, I don't have as much experience as you in the Aegis community, but I'm a member of the proverbial club. I served aboard USS San Jacinto, a Flight 2 Aegis cruiser, and then later supported the Assistant Chief of Naval Operations for Missile Defense and the Aegis BMD program office that we previously mentioned. While aboard Sanjak, I'd never heard of Admiral Meyer, but while supporting on the program side, I was in several plenary sessions where his presence was felt, and I soon learned of what an important figure he was. Perhaps we can compare him to Admiral Rickover, father of the nuclear Navy. But let's start at the beginning. Why was the Aegis combat system developed?
Well, Steve, I got to tell you, we are really blessed to have the history here with the Aegis that has delivered incredible capability to us throughout and paced the threat. We recently had some very serious events in the Red Sea and the Eastern Mediterranean. Our forces were effective throughout, and those are primarily Aegis ships out there doing that mission. So it's as serious today as it's ever been, actually. But we have to go back in time for what the genesis of the Aegis combat system was. You have to go back to a different era where the nuclear clock was at 11:59. The United States and the Soviet Union, the Eagle and the Bear, were struggling. On the one hand was the communist idealistic in the communist culture, where the individual is there for the state, versus our liberal democracies, where the state is there for the individual. Completely diametrically opposed political orientation. And it truly was a struggle for national survival and the survival of civilization. So that was a very serious time. In the late 1960s, there was a man named Admiral Rich, who was a World War II submarine commander, storied history there. Then went into surface warfare, air defense, missiles, as we entered the missile age in the 1950s and 1960s. And he got to his ship, USS California, and it didn't work. The combat system didn't work. Shot a bunch of missiles at targets, and they were not able to intercept those. So we had 3 missile programs, the Terrier, the Tartar, and the Talos. They were safe, but they weren't reliable and they weren't effective. And every system that goes to sea should be safe, effective, and reliable. The acquisition side of the house, the procurement side of the house, owes that to the sailors and the officers operating ships at sea, long departed from their home port, months and months on their own as an expeditionary force. The organization owes that to the ship side, to the operational forces, safe, effective, and reliable. And this is a case where we were not. Exhibit A is USS California. It was not effective coming out of the shipyard. And at that time, we did complex warships, missile ships, a little bit differently. The shipyard was in charge of the physical integration. Okay, fine. The shipyard was in charge of the test program. Okay, fine. The problem was the systems all came together, set in the warehouse at the shipyard, got installed, and all the integration work had to happen there. And this was also the leading edge of our digital world, where we had analog weapon systems, but we were trying to introduce Naval Tactical Data System, NTDS. And so we had to have digital analog conversion, analog to digital conversion. We were starting to get into computer programs, and different groups were tweaking there and optimizing their computer program in their silo. And when it all came together, it wasn't integrated. It did not work. So USS California had an extended time and did not deploy for a couple of years while we tried to fix these issues. And remember, this is a very serious time as we tried to take on new threats. If you flash back to World War II and the end game, we had the first, frankly, anti-ship cruise missiles. They were called kamikazes. They had a human fire control in it. And then missile technology progressed very rapidly through the 1950s and 1960s on the offensive side. And so we had to develop a defensive side to defend our assets. Otherwise, we were going to lose. The United States of America and the free world was going to lose if we didn't have a defense. And then we get to California, and it hit us in the face that we were not as good as we thought we were. And we needed to do better. So Admiral Rich was part of the genesis to set up Nemesis and start working on the 3T program, fixing the 3Ts. And he enlisted a man named Wayne Meyer to help him out at Nemesis. And they were working on the SMS project. So that project really is the kernel of Aegis. And what Wayne Meyer did there was he learned everything that was wrong. And so when you're in the arena like that and things are not going well, but people are counting on you, the Navy and the nation are counting on you, you learn quick, right? And he did. And he started working on advanced concepts. That included, instead of rotating radars, working on phased array radars. And there were several false starts there. on our phased array radars, but then we got to a successful planar phased array radar. He started working on how do we use these computers, because this is a very time critical mission, the self-defense of ships themselves, but also the self-defense of the aircraft carrier. Very important. The United States aircraft carrier remains a power projection powerhouse. It cannot be replaced by Tomahawks. It can't be replaced by a bunch of missiles. You cannot generate the level of firepower from VLS tubes that you can get from a single carrier with multiple sorties. Can't be done. So carriers remain an incredibly important power projection platform for us today. Cold War, nuclear clock, 1159, the centerpiece of our defense, right? Our defense forward. And our whole Navy was structured around, at that time, 15 strike groups. So how do you defend that? And what were we defending against? And this is the one thing that has always centered Aegis. In Aegis, you always start with the threat. And not onesie twosies, right? Real threats, a portfolio of threats. And you design not to the individual threats, but to the most stressing case of all the threats put together. So what we were defending against was massive raids from Russian bombers launched against a strike group. And we were not going to be able to do it unless we could put a lot of defensive missiles, surface-to-air missiles, in the air and get them on target to take down either the bombers. That was probably the outer air battle, that's why we had the F-14 Tomcat back in the 80s, right? But as the threat got closer and those missiles were launched, we had to take them out. And it had to be kinetic at that time. Directed energy, EW, they were, directed energy was far in the future. Electronic warfare and deception, we had some of that, but we had to have kinetic kill. And so we knew what the problem statement was. Wayne Meyer, Admiral Rich, and Admiral Doyle, who was Oppo 3, which is Director of Surface Warfare, they absolutely understood the problem statement. How do we take out massive raids of anti-ship cruise missiles to protect the strike group? Not just the Aegis ship, but the whole strike group. And what are we going to do about it? So Admiral Rich was working the organization piece, because what he saw on USS California was our acquisition side, our procurement arm, was not organized for success. It was too dispersed. There wasn't someone accountable for the system. And this is a really important point, because everybody goes, all the major program managers are major program managers of a system, of this system, of that system. Admiral Rich, Admiral Doyle, and Admiral Meyer had a different focus, that the ship was the fighting integral. That was the system. Nothing less. Now, they made a practical decision to divide that into two pieces. One was the ship. Then we have plus the combat system. And that gave you a warship. And the only reason they were able to do that was there was a very tight connection. And when PMS 400 stood up, it had responsibility not just for the ship part, not just for the combat system part, but both. So there was one person in charge of the Aegis project, which included cruisers and the Aegis combat system, and then later destroyers with the Aegis combat system, in the same program office, using common class equipment, using a common combat system, and really getting a lot of synergy over the whole program. So, and we're talking about the Aegis combat system, but we really need to narrow it down, because we really started with something smaller and more focused called the Aegis weapon system. So let's talk about that. So the Aegis weapon system was the Spy-1 radar. It was the computers, the human interface, and the weapon control system in the middle, and then the launcher and the portfolio of missiles, right? SM-1 and then SM-2. That's it. That was the Aegis weapon system. Why was that important? It was very important because it was procured as a single system, including the Spy-1 radar. It was a Mark 7 Aegis weapon system, quantity 1, that was ordered. And it included the radar, the control elements, and the computing infrastructure, the launcher, and then the missiles were procured separately, but the integration of those missiles was part of this development. Well, that doesn't necessarily make sense to a lot of people today, because typically we're buying systems and then doing the integration. But you have to go back to the time that this was developed in. This was serious business. We were going to lose if we did not have the capability to defend the strike groups forward. And that gave us focus, energy, and a real mission to go after. And they did. And they kept in their mind safe, effective, and reliable delivery to sea. That was motivational, and that was the foundation of what they needed to do. And it came through as we have to design Aegis to sea, right? And some other epics as we go through the Aegis program. So one of the biggest changes that happened during this time, besides the organization PMS 400 being in charge of both the ship side and the combat system side, was how we delivered to the shipyards. Remember, previously, everything went to the shipyard, was installed, tested by the shipyard, and then delivered to the Navy. But it didn't always work, particularly in this complex digital age that we were entering. The big change was to make sure that the combat system was safe, effective, and reliable before it was sent. And I'm not talking about test units. I'm talking about actual production equipment. Went to the production test center. It was set up, the Aegis weapon system, and tested throughout. The actual cables that were going to be installed on the ship were used at the production test center. The actual equipment was used. All the test procedures that were going to be used on the ship were redlined and tested out in the PTC, the production test center. And then once we had a known working good combat system, only then did it get shipped to the shipyard. So at that point, if anything happened, we knew we had a known working good, and it made it so much easier, so much more efficient to track down problems, find out where they were. The test procedures ran smoothly because they'd already been walked through several times. And that turned out, and we had an Aegis test team, which still exists today rather than a shipyard test team, because as complex as NTDS was, Aegis was light years beyond that. So we're blessed to have this, the world's most effective weapon system in terms of self-defense since the 1980s. Tycho went to sea in 1983, and we're blessed to have it with us today. And it is just amazing where we've taken it.
So let's talk about Rear Admiral Wayne Meyer, the father of Aegis. Who was he?
So Rear Admiral Wayne E. Meyer, from the great state of Missouri, which actually is the show me state. So that gives you a little insight into him. He was also the son of a preacher, and he truly believed that you had to talk, you had to communicate, you had to convince, you had to inspire folks that are in the program office. A number of things that he did really has made him an iconic figure in naval warfare and naval construction in the United States Navy. He didn't do it alone, though. Admiral Rich was instrumental in getting the organization PMS 400 authorized and set up. Admiral Doyle, then Oppo 3, in charge of all the requirements, was a warfighter. And he spent a lot of time making sure that the resources were there for Admiral Meyer to execute. But they were in a mind meld regularly on how to take on this very serious problem of defending against large raids of anti-ship cruise missiles launched from Soviet bombers. And that relationship was foundational. So if you go up to Moorestown, there's CSEDS, Combat System Engineering and Development Site. It's named after Vice Admiral Doyle. And then extension was added for Admiral Meinig. But those systems, those centers are critical, and Vice Admiral Doyle was absolutely essential to the Aegis program. Without him, it wouldn't have happened. Without Admiral Rich, it wouldn't have happened. And without Wayne Meyer, it would not have happened. So they really understood strike group operations, and they took it to heart that their mission and their mission alone was to defeat those raids. So Wayne Meyer, to talk about him a little bit more, some people kind of describe him as grumpy, right? And the thing is he felt truly in his heart, he had to get this right or we were going to lose. The nation would fail and communism would prevail across the globe. That's tall order, right? I mean, you can't stay up at night knowing that you didn't give it your all. And so he did. So his secrets of success, from my perspective, remember this is a retrospective, was he had very clear priorities that guided engineering, the Aegis cornerstones. He had very clear priorities on how to get there organizationally, and he had the drive to do it. And he also had a big tent. One of his things was we never throw anyone away in Aegis. If somebody came in for a position and they weren't great at it, they weren't fired, they would find that match, that positional match. And the mandate was Aegis excellence. We deliver Aegis excellence. We are going to succeed because we must.
Tom, tell me, what was the coloring book and what principles did it lay out as the foundation for Aegis?
So I love this. So the coloring book is the first PowerPoint presentation used really as a sales pitch for a weapon system. It showed what could be done with the current technology at that time, and this is in the early mid-70s. It was in color, and back in that time they had view graphs. There's probably not very many people that remember view graphs. Very simple. It's either the first OV1, and if it's not the first one, then it's certainly the second one, but one of the most widely used. And it's amazing that many of the things from the coloring book lived on in different ways. So the coloring book helped him sell the program, and it was based on fact. And it was deep on what could be done to take on this mission of the killing all the raids that were coming in. It had the first OV1, which showed the ship and all the missions it could do. It showed the detect, control, engage pieces, and it highlighted the Aegis cornerstones, which really guided and prioritized the engineering effort.
Let's drill down on this a little bit more. You know, when I think of Aegis, I imagine the three major components: the radar, the combat system, and the missiles that you've been describing that the Aegis system employs. Am I influenced by Admiral Meyer? Am I influenced by that original OV1 if I think about it in this way?
You absolutely are. It goes back to the detect, control, engage. And from that came, yes, the sensor, how to take the sensor data, have the human interact with it, have some automated pieces to it, and then being able to launch missiles and take out targets. That is the Aegis weapon system. And that detect, control, engage, you have to remember at the time, we were starting to get into the supersonic, and time is absolutely the coin of the realm in a weapon system, in a fire control system. In fact, time, or the opposite of it, latency, and controlling latency and understanding latency and time, is the difference between fire control systems, weapon systems, and computer networks. In computer networks, things can get delayed and there's no impact. If data gets delayed in a fire control system, you lose. So there's a very high level of focus on end-to-end timing for fire control systems. And that's why the spy radar, the computers and the human interface, the launchers and the missiles were engineered as one mission thread, which for air defense, right? So detect, control, engage are the right big blocks. What we put in detect, control, engage, those are the right things. We should also mention that's the Aegis weapon system. And then the Aegis combat system is bigger. That's where we add interfaces to electronic warfare systems like SLIC 32. That's where we add interfaces to other sensors, surface search radars, IFF, tactical data links. Those are all kind of on the sensor side, data input side. On the other side, we have the weapons. That's the SM-1 missile at the time, SM-2 missile. We have a whole bunch of missiles now. We'll talk about that. Also the helicopter, because the helicopter was integrated into the Aegis combat system because this was the Cold War. We were trying to beat the Soviet Union, and they were a forward sensor, but they were also a weapons platform for prosecuting submarines and things like that, right? The guns on the weapons side. Then we have harpoons, Sea Whiz, and systems like that also over there. Associated, not in direct control, but for VLS deconfliction, is Tomahawk. We'll talk about that when we get to VLS. But that construct, detect, control, engage, was really, really important. And this is, you can see kind of Admiral Meyer, how do I explain something really complex, the Aegis weapon system? How do I explain its capabilities to people who aren't engineers, to stakeholders that have a veto, what the program and what the project was trying to do? And so it's a communication tool, and it's a darn good one.
Specifically, what were the requirements for the Aegis radar systems?
So the primary requirement was to track anything that was flying in the air. So then you get to the practical matter of how do we do that? So the problem with rotating radars is they rotate around and the radar beam is literally following the antenna. It's too slow. When you have low flying anti-ship cruise missiles, even subsonic, it's too slow. So you have to have then multiple radars, right, to cut for the coverage. Against supersonic cruise missiles, particularly low flying, sea skimming, supersonic maneuvering anti-ship cruise missiles, rotators are completely inefficient. They just are. They're not going to get the mission done. They knew that in the 70s, and that's why they were working on phased array radars. And there was a very key decision that was made for the Spy-1 radar was they chose S-band where it was so that they could balance both the ability to surveil the air defense area, right, that battle space, but also to provide enough fidelity that it was weapons quality information. That's hard to do. They found the right sweet spot. And then phased array and planar phased array became important choices too. So this is the magic of Spy-1 radar. Every Aegis ship has 4 planar arrays, those octagons you see on the superstructure. They don't rotate, they don't move. But somehow, through some fantastic engineering, they can electronically steer that antenna. So part of Wayne E. Meyer's magic is how to explain that, right? And so he didn't get into the engineering details, but he talked about the capability it would bring and the fact that how super effective it was and how reliable it was, because now you didn't have rotating parts. You could A, do the mission, and B, not have to worry about repairing it all the time. And the gimbals and the mechanics and moving mass around, much more difficult. So it was an elegant but super effective solution, the Spy-1. And its job is to track everything that it can see. Now, some of the stuff that it sees are things that could or could not be a vehicular track, right? Vehicular track being a missile or a plane or anything like that. We call that clutter or the land-sea interface. So there are lots of radar returns that are held by the SPY-1 radar and its track file that don't go over to the commanded decision system for the human to interface with it. Why? Because we know it's clutter, and we start working that. And we spent many, many, many years understanding atmospheric clutter, and we thought we were pretty good. And then in the 80s and late 80s and early 90s, we started to deploy to the Persian Gulf. And guess what? Entirely different clutter environment. There's so much particulate matter. And so the good news is we got better on the engineering side, being able to take care of that with the SPY-1 radar. And the operator has some controls there too to make his life easier. At the end of the day, we have a clear picture of the SPY-1 radar. A little sea story on this. So I was on USS Elliott. We were doing a SYNC-X on a Hulk with some aviators out of Miramar. They had first shot, and then we were going to take the next shots with the gun. We'd go in and do that. If at the end of the day, the Hulk didn't sink, obviously EOD, explosive ordnance disposal teams, go in and finish it up. So we're there on USS Elliott. My captain is senior, so he's the range safety officer. The USS Valley Forge is there, Aegis ship. We're getting towards dusk, and we have a great picture, fantastic picture. So I'm able to call green range, and I can see hundreds of air tracks in the LA flight corridor, right? None of them are out in our area, got great track on them all. The aviators want to extend a little bit into dusk to get some night flying because they still have some ordnance left, and they want to take it out on the Hawk. That's all great. Valley Forge, though, has a commitment. So they have to go. So they head south towards San Diego. And we're on our last run. And thankfully, it was the last run, or we were going to have to shut the range down. Because as the Valley Forge started to crest over the horizon, and our data link started to become inconsistent, my picture was disappearing because it hit me like a hammer. I'm not generating these tracks on USS Elliott, a Spruance-class destroyer. I'm getting them from the Aegis ship. And so we finished up, Valley Forge finally over the horizon. Everything's safe, right? Last run done, red range. They crest over the horizon. I lose my connectivity. And I see the picture that I would have had without Valley Forge, which was nothing, hardly. I mean, it was insufficient for me to do my job. And it hit me like a lightning bolt that the Aegis system was darn good and probably great. But it was a very stark difference there within 5 minutes, right? As they crest over, all of a sudden, the picture I had with the LA traffic corridor disappeared because on our system, we had to do a lot more manual work. So that really hit me that Aegis, really good. And then I found out why. It's this Aegis cornerstone thing. And it flows from SPY-1 through the C&D system and the weapon control system over to the missiles, right? And they're timeless. One is reaction time. And this gets to the fact that we start with the threat. We have to understand exactly how much time we're going to have to react. And when you have supersonic sea-skimming missiles, it's not a lot of time, and we have to be able to take out that threat. That becomes the demand signal, right? And we can figure that out. And with computers, you can meet reaction time in a lot of cases, in all cases, right? Coverage. Not acceptable to have gaps in your air coverage, your air defense coverage. Not acceptable. So Aegis designed to provide 360 degrees hemispheric coverage from 0 degrees to 90 degrees in elevation, right? That's what it's designed for. No gaps. Can't let anything through. Firepower. All right, we're not going to have this great system and only have 10 missiles on the ship, right? You got to match what can be thrown at you with what you have to defend. So firepower matters. That was the Mark 26 launcher. Now it's VLS. How much firepower can we get on these ships? Environmental resistance. This is talking about being anti-jamming, the ability to fight through different kinds of jamming, as well as the natural environment. And the natural environment can be pretty demanding all by itself. And then finally, continuous availability. Not a reliability of 90% of the time, 0.9, right? An ASABO of 0.9, an operational availability of 90% of the time. So I love it when I talk about ASABO with folks, and particularly acquisition folks, because for some reason they send around 90% is great. And I have to disabuse them of that, because 90% reliability means that you're down 3 weeks on a 6-month deployment. You're down 18 days with your self-defense system. That's criminal. That should not, we need 0.99, 0.9999, right? So when you kind of put it in that perspective and to remind them that, oh, by the way, the spare part may or may not be on board, but the warehouse is definitely not down the street because they're in the middle of the ocean. And it's going to take days and days, if not weeks, to get the replacement parts. So that continuous availability led to something that's really important. We kind of take for granted today, which is Aegis redundancy. There are very few single points of failure in the Aegis weapon system. Why? Because they knew they were going to be deploying for long periods of time without support. You can only have so many spare parts on board, so you had to build in your redundancy. And so there's often, there's 2 cooling skids. There's 2 sides to each cooling skid. There's 2 sides to the signal processor. There's 3 driver pre-drivers. I won't bore you with the details, right? So as you go through this, you find not only is there a lot of redundancy built in up front on purpose because of this cornerstone, continuous availability. So these guide and prioritize the engineering effort to deliver the Aegis weapon system. Anyway, that was a long answer. Sorry to go into all that, but boy, they are timeless. Turns out they are timeless, and we continue to use them today.
Aegis also saw the evolution from the Mark 26 double arm launchers to the Mark 41 vertical launch systems, commonly just called VLS. What influenced that expansion?
So there were a number of issues that influenced that expansion. The first one was the Mark 26 fabulous launching system, double armed, right? So you could put 2 missiles on, but it was a mechanical hydroelectrical monster with not a million, but hundreds of limit switches. And because I was on a ship with Mark 26 launchers, and that was USS Callahan, which was a new threat upgrade ship, and it had Mark 26 launchers. A lot of maintenance effort to keep those well maintained. And if you didn't, and even if you did, there were always adjustments that needed to be made. They were hard to maintain. That's the bottom line. They were hard to maintain. On top of that was you could shoot a lot more missiles quickly from VLS. So Wayne E. Meyer wasn't convinced about VLS in the beginning. And then as it evolved, and he became a convert to support it, because you could get more firepower more quickly, more reliably. And so VLS effectively sold itself based on its capabilities. And boy, are we glad, because not only do we have SM-2 missiles in there, several varieties, right? We now have the SM-6 missile in there, fabulous Swiss Army knife of a missile. We have Tomahawk missiles in there. We have the Evolved Sea Sparrow missile system in there, and those are quad packs, right? We have the vertical launch ASROC. I talked about how this SM-6 is kind of a Swiss Army knife of missiles. Well, VLS is absolutely the Swiss Army knife of launchers. And it also helped reduce your radar cross-section. That's kind of nice too. So all of that put together, natural fit. Once they figured out the ship integration, which took a while, and the digital integration with C&D and WCS, and the deconfliction you have to do with the radar and the missiles, because when you launch a missile, you have to guide it on defense.
Tom, will you talk for a moment about the difference between offensive and defensive weapon systems?
Well, so the one thing we know is that it's much more difficult to develop a system on the defensive side than the offensive. Just think about it. If I want to hit a point on land, I can either use GPS, I can use terrain mapping, I can use visual TV, but I'm going to a point, the point's not moving, the target is not moving, right? So that's much easier than defense where you're trying to shoot down a missile. This was groundbreaking. The Aegis development and the Aegis project was groundbreaking on the ability to detect, control, engage, launch a missile out. And remember, when we launch the missile, we're trying to do it at range. We launch our SM-2, it's heading out. Well, the offensive missile, the anti-ship cruise missile, it could have pre-programmed maneuvers. It's going to have normal turbulence from just moving through the air at speed. It's not necessarily going to be where we think it is, the predicted intercept point. So as the threat missile maneuvers around, we have to be able to accommodate that on our side. So really, you need much more maneuverability for a defensive surface-to-air missile than you do on the attack side. That fundamentally changes the engineering. You have to have better missiles. You have to have more agile missiles on the defense side. And you have to have the ability to control them. Even today with SM-6, if we launch it and say, and it has an active front end, right? And we say, go find the target at, X number of miles, it can't do it. That's a little tiny radar, right? It's a little tiny radar compared to, the 12-foot SPY-1 or SPY-6 radar, right? Which is surveilling, a couple hundred miles and tracking all those targets. So the missile needs help to a certain point. Now, there's a certain point on active missiles where they can take over for terminal and to consummate the intercept. Prior to that, though, we've been using SM-2s, so we have to help the missile. One, we have to tell it where to go. We have to do the calculation for the predicted intercept point on the ship, give acceleration commands and guidance control commands to the missile. It follows those. And then in the end game, we have to give it a little help, something to home in on. And we do that with illuminators, and then they home in on the return signal. So it's just, all of that was groundbreaking at the time. And what that allows us to do, what Aegis also brought was the ability to put a lot of firepower up quick. Because before Aegis, it would be one missile at a time per illuminator or director. That was it. So you had 3 directors or 3 illuminators, you could take on 3 targets, period. And until that was done, you couldn't do any more. Aegis, we timeshare the illumination. So that allows us to put a lot more missiles in the air. That's really important when you're trying to defend against a raid. And the other thing that Aegis brought was layered defense, right? We're going to shoot at long range. We're going to shoot at intermediate range. We're going to shoot at short range with SM-2s. Then we'll take on with CWIS and the gun. And then finally, the captain on the starboard bridge wing with his 45. That's the last piece of defense, right? But just the amount of firepower, your ability to trite the raid over time and battle space wasn't just an improvement. It was revolutionary. And it remains that way today.
Let's go back to Admiral Meyer. This podcast is entitled Talk a Little, Learn a Lot, as an homage to Admiral Meyer's motto, build a little, test a little, learn a lot. I know this tells a little bit of the story of how the Aegis combat system was developed. We talked about this a little bit in the front end of the podcast. But please unpack this a little bit and what was meant exactly by that motto.
So if you go back in time, it's early 1970s. We've learned a lot on the missiles out of the SMS project to fix the 3T issues. And were working on phased arrays, and it was, this is new. And trying to put together this Aegis weapon system was new and very difficult to comprehend the whole at a high level of detail, engineering detail. So, frankly, incredible and very important decision was to take Norton Sound, an old airplane tender, right, and convert it into a test ship and keep working it. And they made lots of trades, engineering trades, based on what they learned on Norton Sound. They also shot a lot of missiles in test to verify that phased array would work. It would work both for surveillance and for fire control. And they really were very dedicated to making sure that each and every technical question mark was answered. And then that was reflected as they stood up CSEDS, the Combat System Engineering and Development Site up in Moorestown, as well as NSWC Dahlgren, the Aegis division there, department there, to get into the computer programs, be very judicious. And there were always these set points to actually do just that. We're going to build a little, we're going to test a little, and we're going to make sure we know exactly where we are, right? And a lot of that was configuration management, but a lot of it was just, we don't know what we're going to find out. And so knowing your limitations up front brought out this build a little, test a little, learn a lot, so that they could actually educate the workforce, learning organization, and they could answer all these technical questions and engineering dilemmas piece by piece by piece. And it worked. And today, if you flash forward today, and if you get into agile software coding or agile project management, that is the logical conclusion of build a little, test a little, learn a lot. Agile software development, what do? You work on a function until it's done, and you know it works. And then you go to the next one. You don't do a bunch of things in parallel and hope they all come together and work, right? You architect the system so it can be built in stories, right? And so you get story points, right? And only so many story points can be done during an agile session, right? And you get that function done. And if you don't get it done, you don't move on. You just schedule it for the next sprint to be finished, and you get it done. And remember, we're humans. So if we try to take on too much, we lose the context of the detail that we're working on. And so they had the architecture, and now they are working their way through it very meticulously. In fact, there's a F squared D squared, which was a room up in Moorestown where they laid out all the communication protocol between SPY, CND, WCS, and the launcher. Every computer message was laid out. Which ones had to be confirmed with a receipt? What was the timing that was required? All laid out. But then when they got to, so they laid out the architecture, they laid out their specifications. And then when they went to code, they went and started coding it up, right? But build a little, test a little, learn a lot. Sage advice when you have a large, complex, multidimensional project, there's a lot of unknowns. You know, you're going to have a lot of very detailed technical engineering questions to resolve along the way. Well, we often get ahead of ourselves, right? But the commitment to get it right was so foundational in Aegis, and to do it with excellence, that I would submit to everyone that build a little, test a little, learn a lot still applies today.
Admiral Meyer had some other axioms too. What were some of those beyond build a little, test a little?
So one of them is the devil's in the details, right? And that speaks to the complexity of any major system that we have today, whether commercial or whether, a weapon system on a warship, because the devil is in the details, right? And integration, right? Integration. We're going to build an integrated weapon system. And when you focus on the integration, it becomes really important. We've often tried to just give people the same standards and say, oh, you have the same standards, so you'll be able to talk to each other. Well, we know with Link 16, where each service developed their own Link 16 systems and their own protocols inside, all to the standard. In the beginning, there were plenty of issues to resolve the poor interoperability at the joint level, right? But those get resolved over time. But certainly, everybody thought, hey, we have a standard, good to go. And a standard's not enough. You have to get down into the details and actually do that engineering. Same thing with innovation. Oh, we're going to innovate. Great. Guess what? You're not going to deliver anything unless you execute and do the engineering. Innovation is not a substitute for engineering. It's not. You can innovate with ideas. You can innovate with taking different things and putting them together, or extending the mission, right? So we've extended the mission of the Aegis weapon system into ballistic missile defense, and now hypersonic missile defense on the search and track side, going into the kinetic side with the glide phase interceptor. That's out of the Missile Defense Agency. We've extended SM-6 to prompt sea strike and other missions. So that's great. But there comes a time where you have to take your innovative thought and engineer it. And when you're dealing with weapon systems, the bar is just higher. There's a lot of talk about emulating Silicon Valley and the minimal viable products that they put out for apps and other things like that. I think that's great, except for when it comes to a weapon system. I think the acquisition side of the Navy owes it to the men and women wearing the cloth of this nation to deliver a safe, effective, and reliable system. I can't get off that stage that's actually the minimum. The minimum viable product is one that's safe, effective, and reliable if it's a weapon system. Now, there's ways to do some prototyping. There's ways to do some testing. There's ways to add, software modules so you can try it out with real sailors. That's all good and healthy. But I'm talking really about this fire control stream, and this fire control mission thread, right, that we pull through. That's kind of sacred. We got to be careful when we dive into that. It's okay to dive in ashore and testing to see if we can get a new capability or do something like that. But let's be careful before we assume that we got it right. Let's make sure we got it right. Let's know that for the fire control piece of the weapon system. I would appreciate that, right? For being on ships for 10 years, right? I would appreciate knowing that we're delivering safe, effective, reliable fire control loops to all our ships. Really important.
Many of the ASNE listeners likely grew up in a digital world. Maybe their entire career has, in fact, been on an Aegis ship. For perspective, how is the Aegis system different from its predecessors at the watchstander level?
So the first thing is there's a lot more automation in the system, the Aegis weapon system, than there were in CDS, ACDS, new threat upgrade. So that's the first thing, and the most important. Two, you had the ability to move around from console to console and kind of take your mission with you. There's a couple consoles that have associated equipment that make the tactical information coordinator, for example, that kind of keeps that station there. But you have flexibility. That's important. That becomes really important as you flex from one mission area to another. Whether you're doing ASW, you're always doing self-defense, but if you're also doing ASW, then you have the room and the flexibility to do that mission. And sometimes you'll have flex consoles where if you're doing ASW and helicopter control, then you'll devote that console to that mission area. But if you're doing a lot of air control and you have your aircraft control supervisor and his AICs, air intercept controllers, maybe you have another console there. So it gives you the flexibility on the operator side and the watchstander side to move around. Then you have the command element. Absolutely revolutionary from a command information center historical perspective. Now you had the commander, the commanding officer or the Air and Missile Defense Commander, the warfare commander, plus his tactical action officer, plus some assistants, plus force, all looking at the same picture, the large screen displays. It was so good that when the commander of operational test and evaluation went on board to evaluate it, he said this was the best range control center he would ever have at the time. That was when it first came out, and that was on Tycho. So, in fact, he was doing range safety from the cruiser because the picture was so good, and it was shared. On the large screen displays, the command element had the same picture, and they could literally both point at the same track, as officer to officer say, "I'm talking about that track." They could hook it. They did lots of different ways to do it. The wonderful laser pointers came out, and they became an indispensable tool for the commanding officer to make sure everybody's talking about the same track, right? But that was revolutionary, just to have that visualization. That has spread, and in fact, in lots of ways, it's become more and more of a tool as we recognize words and sentences and paragraphs are fantastic. Words and sentences and paragraphs with visualization, the coloring book, is the best because we're visual beings, right? So that's the change from, those are some of the big changes from the operator perspective. Automated their workload to a large extent. You could evolve the system to meet new missions. You could adjust your watch standing and watch standards based on the priorities of the day and the different missions you were doing. And your command element was always in sync and outfitted with just great comms with everybody. That was very different. That was very different from the previous CICs.
This has been a great conversation about Aegis, about the father of Aegis. I want to now focus back on the new digital publication that's coming out, The Story of Aegis 15 Years Later. So in broad terms, please relate to the audience what the new version of this this history is all about.
Yeah, as we looked at the 2009 Aegis edition of the Naval Engineers Journal, it became very clear we have done so much since then, and there's enough new material to inform everyone of the new status and the new level of Aegis. So I'll go through a few of them. I'll do capabilities first, and then I'll do the piece that kind of helps us deliver that capability. So in 2009, NIFCA, Naval Integrated Fire Control Counter-Air, which is where we're using a smart missile and third-party targeting to shoot over the horizon and start attriting that raid of anti-ship cruise missiles as a force layer. So we have self-defense layer on Aegis, of course, every ship does. Then we have the area air warfare layer ranging, and that's where we protect the carrier and other ships in our immediate. And now we have NIFCA, which provides force level, literally over the horizon. That was innovation backed up by a massive engineering effort to deliver that capability. Wow, it added a whole new layer of defense. It bought us battle space and it bought us time. So NIFCA, hugely important, and just an incredible capability. We have prompt sea strike now, right, with the SM-6 in the surface mode, and it works really good. So we should all be happy we have that capability, which we didn't have before. We had BMD in 2009 with an urgent capability in the SM-3 Block 1A. Well, we've advanced to the SM-3 Block 1B. It's a better missile, has a better seeker, leads to better intercepts. And then we added a new missile, SM-3 Block 2A. The SM-3 Block 2A is not a replacement for the SM-3 Block 1B. It is longer range, and you use them for different missions. But today, we have 2 Aegis ashore sites, yes, We took the Aegis weapon system and put it in a building, one in Romania and one in Poland, and we outfitted their launchers, their VLS launchers, with SM-3 Block 1Bs and 2As. And what that allows two sites to do is defend all of Europe against ballistic missile threats coming out of Southwest Asia. Now, I'll have a little segue here. The Russians complain about them sometime. It's all propaganda. The reality is any ballistic missile coming from Russia into Europe is going to be at a much lower altitude. It's not going to get in space. These missiles are only effective in space. So that's all hogwash and a distraction. And the Aegis Ashore sites were designed within the treaty limits and agreements of the time. So they have no AW capability. They're BMD only, and they're focused on the threat out of Southwest Asia, Middle East kind of area. So we advanced hugely our capability with the SM-3 Block 1B and the SM-3 Block 2A for ballistic missile defense. In fact, with the SM-3 Block 2A, we shot down an ICBM, intercontinental ballistic missile. So that's an extension, right? So that was pretty cool exercise and test event we did there. So we've extended our BMD battle space. We have also added hypersonic missile defense, which is search and track today. So we can see them, we can track them, we can pass that information to lots of people. We have some capability with sea-based terminal with the SM-6, which is a pretty close fight. So we want to add a layer so we can get at those hypersonic raids further out. And that's the glide phase intercept program down at the Missile Defense Agency. So we've done those are all new missions for the Aegis combat system and the Aegis weapon system since 2009. The other very important thing is that we went to a common code base for Aegis, and that was part of the advanced capability build for 2012. When that happened, we established the Aegis Common Source Library. That's a common code base. Out of that, we forged a whole bunch of baselines for a whole bunch of ships. Same code base. New construction destroyers, modernized cruisers, Aegis Ashore, Combat 21 on LCS, Coast Guard Athena program, Japan, South Korea, in the future, Australia, Canada, Spain, all from one code base. There's a lot of configuration management that goes along with that. Very detailed, because they have different radars, they have all these platforms, they have different radars, different weapon systems and things like that. But that gave us a lot of synergy, and it provided a lot of stability to all the shipbuilding programs, and just was foundational to be able to add these capabilities and have them flow out not to 2 or 3 ships, but to a whole bunch of ships. Right, that whole portfolio of warships that I talked about are sourced from the Aegis Common Source Library. That's pretty great, and that's incredibly efficient, frankly, because once we fix something, we develop a capability, or we fix something, we can put it out. Now, because they're running on different computer systems and they're running on different architectures across those ships, yeah, we have to do extra testing in certain cases to accommodate the differences between the ships, but again, I've said safe, effective, and reliable a number of times. That comes from Admiral John Ailes, as those have got to be our priorities, which I totally have absorbed and agree with. That's also required here to make sure that each ship gets a safe, effective, and reliable system. But there's more. We have done even more. We've connected with Space Command, and we're working with them because ships are sometimes in the area of the world where all our ground-based radars aren't, and our radar can see satellites. So sometimes Space Command wants to update the tracks of certain space objects, and we can help there, so why not? It's no risk to the ship. It hardly uses the radar at all, and you can do those missions. So I expect that to grow over time. We have a lot more data coming in, data networks, and we have something called Aegis Speed to Capability, ASTOCs, and that's where we'll take on a deficiency, a limitation, or a mission gap or capability gap, and we'll focus on that. We'll use digital engineering, and we'll deliver, we'll do digital testing, digital engineering, we'll integrate it into the code base, and then it can flow to those ships. That's been incredibly important for some of our Red Sea operations, that ability to really focus on a corner of the design space where we have a deficiency or limitation and just fix it. So all of that's happened since 2009. That's a lot. Oh, by the way, we've also developed the SPY-6 air and missile defense radar, and that's now on Flight 3s, right? So we have Flight 3 with Aegis Baseline 10 and the SPY-6 air and missile defense radar. That's fantastic. And Aegis is also part of the architecture for Guam. The Army has the cruise missile defense mission, and Aegis, because we already do it and have been doing it for a long time, so we know it's effective, we will have the ballistic missile defense and the hypersonic missile defense missions. That's a good division of labor between the Army and the Navy, given where the systems are today and how effective they are. And so we're actually putting the two best steps forward that we possibly could with that division of labor for the defense of Guam. Again, that one will be an Aegis baseline and the TIPI-6, which is another solid state phased array GAN radar based on long-range discrimination technology out of the long-range discriminating radar up in Clear, Alaska. So there's some cutting-edge things that have absolutely happened since 2009, including new missions, new capabilities, how we got there, the Common Source Library code base, and then some of these other issues where we're working with partners and joint and coalitions and international. Frankly, it's just amazing. It's been exciting.
So there's going to be a lot to add into this next edition. I thought we would talk for a minute about the Naval Engineers Journal. Have you ever written for the journal?
So, Steve, I haven't written for the Naval Engineers Journal, but I do read it. And I read it because it keeps me current on a lot of things. There's a couple pieces that I really appreciate. One is tools or approaches or methodologies that help decision makers. So in the Naval Engineers Journal, sometimes you'll see something about set-based design and the approach to help decision makers quickly get to informed decisions. And what I like about articles like that is it takes the decision maker beyond PowerPoint, right? And it actually gets to the details and the trades. And those are so important that the trades are understood by the decision makers at a technical level. This is really relevant today as we talk about DDGX. Naval architecture is unforgiving, and every decision has a cost or a price associated with it. A great example is speed. It takes one engine on an Arleigh Burke class destroyer, you can go around 20 knots, right? One engine, trail shaft. On 2, you can get above 25, right? On 3, you can get close to 30, right? And with 4, you can go 30 knots, right? Why does the addition of one engine only give you a little bit more speed? And the reality is has everything to do with hydrodynamics, and that is just an unforgiving environment. So if you want to change your requirements to go, okay, 25, 26 knots, that's fine. The engineers will go off and design a ship with that. It'll probably have 2 engines. And then later you go, oh, I really like it to go faster. Let's say 31, 32 knots. Oh, it's a massive change. Like we just want a few more knots. Why is that such a big deal? Because you just added 2 or 3 engines, at least 2 for sure, no question about it. And that speed piece in naval architecture, it's the length of the hull, because all the friction's up on the bow and on the stern. You get the laminar flow along most of the hull. Those are important details because They drive big costs or schedule as you go along. So that's where Naval Engineer journals and articles about design in particular and helping the decision maker, because naval architecture and naval engineering is so unforgiving, it's just really helpful for the decision makers. They should make no assumptions. The reality is a modern warship, about 15% of the tonnage is mission suites and mission systems, right? Why? It's a floating city, right? It just is. And you got to accommodate for all that. And it also leads me to talk a little bit about, we have miscategorized our ships, right? If you think a DDG or a cruiser weighing in at 9 or 10,000 tons is a large surface combatant, I am telling you that is not true. It is not large at all. They're tiny compared to World War II heavy cruisers, definitely tiny compared to battleships, super tiny compared to 200,000 ton tankers and cargo ships today, right? So 9 or 10,000 tons is not a large surface combatant, and yet we created that language, right? Which, well, large is as big as you can get, right? So now we have Zumwalt, or we want to build a DDGX that's going to weigh in at 16 or 14 or 12,005. People are like, hey, that's too big, right? I thought large was 10. No, it's not. So it's a great conversation. And some of that comes out in the Naval Engineers Journal. The other ones I like to help me keep current are a couple. One, I love all the stability stuff, right? And a high weight, because if you're a program office and you're not familiar with naval architecture, then you have no concept of the impact of putting your system on the mast or high up. High weight is dangerous if it's done irresponsibly. Requires engineering, so you understand the impact. Hey, I'm going to add FXR to the mast. Okay, great. We'll get an X-band radar. Do we know what it's going to do to the ship's moment, the righting moment? That's what keeps you from flipping over and things like that. Really important that kind of work get done right up front. Anytime you're talking about high weight, new systems going on the mast, new systems going high up on the superstructure, you're impacting the stability. We need to know that answer before we get too far down the road with some of these systems. So I love all things stability. Hull design. And I remain amazed that we haven't done more with the swath hull design. We have those on the Tagos, but that's it. But it's super stable, a lot of deck space, really ideal in a lot of ways for naval operations. But we've chosen not to do that. I think there's some hesitation on the naval architectures that we just don't know enough. Okay, I accept that. So let's go find out. And so every time I see new hull designs in here, whether it's a trimaran or a hull design, a swath or something like that, love that. The material science piece in here. I'm so happy that the United States Navy made the very prudent decision to build Arleigh Burke-class destroyers out of all steel. We should be proud of that decision. It has extended the life of those ships. It has increased the safety of those ships because steel melts, aluminum burns, right? And it takes away all these corrosions and bimetallic issues. And you see that flavor of material science in the Naval Engineers Journal. So I love that. And the last one is the modeling and simulation, which is getting better and better and better, both for naval architecture, but just in general, we're getting closer and closer to that nirvana of physics-based models. We're almost, we're like almost on the precipice of having our model be very, very good and very, very accurate to the physical environment, right? And so the Naval Engineers Journal allows me to keep up with those kinds of advancements within our Navy domain. And I just think that's important, right? Stay current, because you don't know what you don't know. World's moving fast. Technology is advancing. And, AI we'll have some missteps. I have no doubt we'll have plenty of missteps. But it will make these kinds of efforts, modeling and simulation, even more accurate and maybe quicker. So it's something to watch. Naval Engineers Journal helps me watch them.
What do you hope to see in future editions of the journal?
So really, I love the hull designs, because we need, if we have questions about different hull designs, we need to go answer them. And that's up to the community to kind of self-assign that, because it's not being directed, right? So we're not doing a lot of prototyping or experimentation with different hull designs. I think that's important. This advancement in tools, I think, is also really, really important. Now, don't confuse my modeling and simulation with model-based system engineering, right? Model-based system engineering is great if done properly, and that means a fair amount of time and a lot of money if you're going to do it properly. It's not cheap. A lot of people want it to be cheaper than our current engineering approaches. I don't think it is. I think it's more expensive. Why? Because you got to get down to the physics level of to really have model-based system engineering. Now, you could have model-based mission engineering. You can have model-based, mission assessments and capability kind of things. All good. But if you're going to really use it as an engineering tool, it's got to replicate the physicality of the system as well as the computer programs and software that runs on it. So I like to see more of that. And then we're going to have to crack open the AI, right? What is the appropriate use of AI in naval engineering? Where is it being used today? Where's the right place to experiment and prototype, which we rely on students and doctors like yourself and people to really advance the state of our knowledge? And where can we use AI to do that? I think that should be a new flavor and something to watch for in the Naval Engineers Journal. So those are kind of the things that I'm looking for. But I wouldn't throw out anything, right? It's important not to lose what we have.
Is there anything else that you would like to share with the Talk a Little, Learn a Lot audience?
Well, the last one is in December, ASNE is sponsoring the Combat Systems Symposium. That is a fantastic forum. Program Executive Office for Integrated Warfare Systems, and probably the Aegis BMD, those program offices often send reps. Great panels there from people who are in the arena trying to deliver capability today. So I would just encourage folks, if you want to get current in a couple days, that is the best place and the best way to do it. So the Combat Systems Symposium this December, sponsored by ASNE. Thanks.
Thank you, Admiral, for taking this time to discuss the Story of Aegis 15 years later, the digital edition to be released in the spring of 2025, and your thoughts on the Naval Engineers Journal. I hope we can welcome you back in the future to Talk a Little, Learn a Lot, the podcast of the American Society of Naval Engineers, to discuss these and other relevant topics.
Okay, great.